main objectives of this experiment are to determine kinetic parameters for the growth of E. coli in LB and M9 media. M9 media uses minimal amounts of salts and nutrients, while LB media is richer in nutrients. Experimental data will be given to us for M9 media. The two main parameters we are interested in are the maximum growth rate and Monod constant. We will then compare the maximum growth rate for each media. In prior testing, the mixing speed was 200 RPM. For our experiment, we decided to raise the speed to 250 RPM. The major equipment we will be using is an autoclave to sterilize a bioreactor and glassware, the bioreactor itself, and a tabletop shaker.
The three equations shown will be used to find the maximum growth rate and the Monod constant for M9 media. They will be derived and explained later on in this video.
There are four main phases to the life cycle of bacteria. The first phase is the lag phase, in which the cells are placed in the media. There's a lot of cell activity, but no growth yet. The next phase is the exponential phase. Here the cells begin to grow through cell division and the quantity of cells increases. From the exponential phase, we enter the stationary phase. At this point, the cell growth starts to plateau as the amount of nutrients becomes depleted. The final phase is the death phase. The number of living cells decreases rapidly as the nutrients become sparse and the waste products grow.
Before beginning this experiment, there are some extra safety precautions needed since E. coli is a biological agent. PPE should always be worn when working with the bioreactor. When leaving the reactor bench, you must throw away your gloves and wash your hands. All trash accumulated must be thrown away in a separate trash bag. All contaminated glassware must be placed in a wash basin. Before and after working with the bacteria, spray down all surfaces with 70% ethanol solutions. Finally, place all needle and pipette tips into the SARPS container within the lab.
Disconnect the bioreactor, remove the lid, and move it to the sink. Using soap and water, scrub down the inside of the bioreactor. Also, clean any surfaces on the lid that will be contained within the reactor. Next, cover all open holes on the bioreactor with aluminum foil and place a piece of autoclave tape across. Clean all the glassware that will be used during the experiment with Alkanox and water.
To make 1 liter of LB media, weigh out 20 grams of LB broth and pour it into a 1 liter glass bottle. Then bring it up to 1 liter with DI water and shake vigorously. Finally, the cap is placed on loosely to avoid the high pressure of the autoclave. To operate the autoclave, make sure there is a sufficient amount of water inside. Fill each basket with the items needed to be sterilized, making sure all are taped and covered with foil. Next, carefully place the basket in the autoclave, replace the lid, and hit start.
First, calibrate the pH probe. After calibration, sterilize the pH and DO probes for 15 to 20 minutes in the fume hood with UV light. To prepare the inoculation flasks, add 0.5 milliliters of E. coli to 60 milliliters of media in each flask and recover with foil. Place the flask in the benchtop shaker, set to 37 degrees Celsius and 200 RPM, and note the time.
To start, add media to the bioreactor and set to the correct mixing speed and temperature. Make sure both control settings are set to PID before starting the experiment. To begin E. coli growth, pour 50 milliliters of the inoculated bacteria into the bioreactor using the sterilized funnel. Immediately extract 1 milliliter from the reactor using a syringe. Place it in a clean cuvette and measure the absorbance at 600 nanometers. Before beginning the benchtop shaker, fill each 250 milliliter flask with 100 milliliters of fresh media and pipette 2.5 milliliters of the inoculated bacteria into them. Immediately extract 1 milliliter from each flask using a micropipette. Place it into a clean cuvette and measure the absorbance at 600 nanometers. Set the benchtop shaker to the desired mixing speed and place the flask inside to begin cell growth. Collect the optical density readings for the bioreactor and benchtop shaker flask every 30 minutes. The video shown illustrates how a reading is taken for the benchtop shaker. If the readings on the spectrophotometer goes above 1, dilute the next sample taken with fresh media. Be sure to note the dilution. Once the measurements have stabilized for an hour, the experiment has completed and the results can be compiled.
In this experiment, we determined some of the kinetic parameters for the growth of E. coli. Some of the relevant equations expressed earlier can now be rearranged into more useful forms. Starting with the change in biomass concentration with respect to time, where biomass concentration is expressed by x. Rearranging this equation and integrating the equation from initial biomass concentration to the biomass concentration at some time t, we solve the equation and simplify it to isolate mu, which is the growth parameter. To solve for the maximum specific growth rate, mu max, we need to look at the biomass optically using the cell density in a UV-Vis spectrometer set at 600 nanometer. When looking at the absorbance values, we see that the initial absorbance value can be expressed as the initial biomass concentration x naught, and the rest of the absorbance values can be expressed as the biomass concentration at some time t. Using the equation for mu, we can now find our mu max by looking at the different mu values and finding the maximum value. Determining the maximum specific growth rate, mu max, visually, we can plot a semi-log plot of optical density versus time. And the reason this works is we can expect the bacteria growth to be in their exponential phase by the time we start taking data. Looking at this plot, we want to find the point where we find the largest slope, which here would be the first 3 points. Using these 3 points, we can then plot it separately and do a linear regression of the first 3 values of optical density for the maximum slope, or mu max, for the bioreactor. Using this, we see that the mu max is approximately 1.26, which does match our numerical solution as well. Calculating the maximum specific growth rate for the shaker top flasks is the same process numerically. Here, we will look at the initial absorbance value at 600 nanometers as the initial biomass concentration, x naught. The rest of the absorbance values are then expressed as the biomass concentration x at some time t. Using the equation for mu, we can then plot all the mu values and extract the largest mu value as our mu max. Obtaining the maximum specific growth rate, mu max, visually for the shaker flasks is the exact same as well. Here we do a semi-log plot of optical density versus time. We isolate the points where we expect the largest slope to occur, which in this case are the first 4 points of this plot. We then plot those first 4 points separately and do a linear regression to extract the mu max. Here we're using the first 4 values of the optical density for maximum slope, mu max, which is approximately 1.17. When dealing with the M9 media, it's necessary to go back to another relevant equation expressed earlier, the change in substrate concentration with respect to time, which is equal to minus mu x over y sub x over s. Here, y sub x over s is the maintenance coefficient, which is approximately 0.5 for the experiment. If we rearrange and take the integral of this equation from initial substrate concentration to the substrate concentration at time t, we can solve and isolate S, the substrate concentration at some time t. Here, the initial substrate concentration, S naught, is the initial glucose concentration used in the M9 media data. Using the given M9 media data, we have the adjusted absorbance at 600 nanometers versus time, using the initial absorbance value as our X naught, initial biomass concentration, and the other absorbance values as our biomass concentration, X, at some time t. We are then able to calculate the mu and S values based on the given data. Looking at our mu values, we can then find the largest value and call that our mu max. The M9 media data can be described using Monod-type kinetics. Using Monod-type kinetics, we see that the relevant equation, mu, is expressed as mu max times the substrate concentration over Ks plus S, where Ks is described as the Monod constant. If we take the reciprocal of mu and simplify it, we can put it in a form that is very useful for us in terms of graphing. If we compare this equation to the traditional linear equation where y equals mx plus b, we see that the slope would be the Ks over mu max, and the y-intercept or b value would be our 1 over mu max. If we plot 1 over mu versus 1 over s, we can then extract the slope value and the y-intercept by doing a linear regression of the data points. Again, the slope value, 0.6098, relates to Ks over mu max. The y-intercept, 1.3542, is then equal to 1 over mu max. We can use the y-intercept to solve for mu max, or we can use the mu max we got numerically to then solve for Ks in the slope. Solving for the substrate affinity constant, which is also known as the Monod constant, we get a mu max of 0.91 numerically, and using that value to solve for Ks, we get a Monod constant of 0.55. If we use the graphical method, we'll get a mu max of 0.74 and a Monod constant Ks of 0.45. Comparing the kinetic data is the goal of the experiment, and we see that the M9 media has a lower mu max value of 0.83 when compared to the LB media, which has a mu max of 1.21. The conclusion is then that the LB media has a larger maximum growth rate value than the M9 media due to its nutrient-rich nature.